Let me tell you a little story. 200-something years ago, there was a pretty darn good mathematician named Carl Friedrich Gauss, and his name is all over mathematics and physics, other things too, statistics. And there's a story that goes when he was in either kindergarten or first grade, the teacher wanted to keep the students busy so he could look at Netflix or something. No, they didn't have Netflix back then. I don't know. Well, he was doing whatever he was doing. He wanted to keep the students busy, the little kindergartners busy. So he told them to add the first 100 counting numbers together. I think that would do it, right? That would keep them busy. But the story goes that little Carl Gauss came up in 5 minutes and gave him the answer, and it was right. Nobody knows exactly how he did it, but this is one possibility. Now, by the way, I don't know how any 5 or 6-year-old would do it, but this is how an adult brain would do it, and his brain apparently was accelerated. So you could write out the sum, and we're going to use this notation, S for sum, S subscript 100, to add 100 numbers together, essentially. So S sub 100, in this case, is going to represent the sum of the first 100 counting numbers. By the way, the counting numbers are an arithmetic sequence, right? What are the counting numbers? 1, 2, 3, 4, about the simplest one you could think of as far as arithmetic sequences go, right? So what's the common difference? D equals 1. So yeah, okay, that's why we're including this in this section. So add the first 100 counting numbers together. Okay, if you were to write at least part of that sum out, it would be 1 plus 2 plus 3 plus 4. Okay, we're not going to do everything, so let's go plus dot, 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 plus eventually you get to 100, right? So we think what little Carl Gauss might have done is written it this way and then written it in reverse, because they both equal 100, whether you add from 100 to 1 or from 1 to 100. So S100 also equals, okay, now start with 100. 100 plus 99 plus 98 plus 97 plus dot, 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 plus, eventually you get all the way down to 1, don't you? Do you remember when you were solving in your other math lives, in other classes, you were solving systems of 2 equations, 2 unknowns? Do you remember you had to, in some methods, you eliminated a variable by adding the equations together? Does that sound familiar? Well, I just created 2 equations, right? I could add them together, couldn't I? So take a look. If I add the left-hand side together, I have 1 times S100 here, 1 times S100 here. If I add vertically, what do I get? 2 times S100, adding like terms, right? Now I want to add vertically throughout. So if I notice what happens. If I add vertically to each of these terms, what do I get? Every single time I get 101, right? So 100 plus 1 is 101. 99 plus 2 is 101. 98 plus 3 is 101. Every single time I get the same number, 101. Even on the very last one. Now, how many 101s are we adding together? 100. It's repeated addition of 101 100 times. What's another way to think of that? So there's 100 terms in the addition here. So repeated addition is associated with what operation? You have 100 101s. You could rewrite this as 100 times 101 on the right side. We think this is what little Gauss did. I can't imagine my 5-year-old doing this. And then all you have to do, I mean, it's relatively simple arithmetic from here, because what happens when you multiply, if you switch the order, 101 times 100? You get just a couple more zeros on the end, right? So you get 2 times S100 equals 101 with 2 more zeros, so 10,100, right? Everybody see what I did? Just this. And then if you want S100, which is the sum of the first 100 counting numbers, if you want to get that by itself, what do you do with this 2?
Divide it out.
Divide. You get 10,100 divided by 2, but what is that? 5,050. We don't even need a calculator. That's what little Gauss came up with. Okay, well, he had his PhD by the time he was like 18 or something, so he might be a little more advanced than us, but we think that's how he did it. We don't know for sure. Sometimes geniuses don't think the same way regular people like us do. So maybe he did it in some other way. But either way, a 5 or 6 year old coming up with this, it's pretty incredible. So why do I mention that? Well, we're going to find the sum, a formula for the sum of the terms of an arithmetic sequence. And it's a more general formula than what we just came up with because it could be any arithmetic sequence. Before we do that, by the way you come up with that formula is much like what we think Gauss did. So that's the reason for the example. Before we do that, I need you to recall something. The sum of the terms of a sequence is called, it also begins with S. Does anybody remember it? It's a series. If you sum the terms, the numbers in a sequence, it's called a series. And so generically, we used this notation last time, sigma notation, n equals 1 to, or I might have used n as the top number last time. I'd have to, the way I notated it here. Sn, the sum of the first n numbers in the series. You could use I or K down here, and then A sub I. So remember, and what that notation means is just A1 plus A2 plus A3 plus ... all the way to AN. Remember we talked about that last time? Okay. Turns out, for an arithmetic sequence where you add the terms together, so an arithmetic series we would call that, turns out there's a formula for that. For a general arithmetic series, Sn, which stands for the sum of the first n terms, let me make sure that's clear. Sum of the first n terms. It turns out if you use that technique that we just used to find the sum of the first 100 counting numbers, same technique, but on a generic arithmetic series, you get this formula. I'm not going to bore you with the details. It looks a lot like what we just did, though. N divided by 2, and then in this quantity, in the parentheses, A1, the first term in the series, plus AN, the nth term in the series. This is the formula for the sum of the first n terms. It works as long as it's an arithmetic series, as long as there's a common difference between each term. We could check it on the sum from 1 to 100 real quick. So we could check Gauss's work real quick, or our work real quick. When you take 1 plus 2 plus 3 plus all the way to 100, so let's try to use the formula right here. What would n be? 100. N is the number of terms, so it's S100 that we're finding. So I should have made that S100 right there. So it's S100 equals, okay, you told me n is 100, so 100 over 2. So we're seeing if we get 50-50 using this formula, 5,050 using this formula. That's what we got earlier. So 100 n over 2, that's what the formula says. What's A1 here? 1. And then what's an here, which would be A100, right? N is, in this case, n is the last term, or n is the location of the last term, rather, in the series. So what would that be? A100 is what we're plugging in right there. And that would actually be the number 100. And you can see exactly what we got before deriving it the long way when we added the two equations together. We get 100 times 101 divided by 2, which is going to be the same number we got above, 5,050. But this formula works no matter what D is, and no matter what A1 is. This formula will work every time.